Chapter 6 moves on to discussing a new type of sequence, in particular, what happens when you take sequences of functions. So, to get some motivation for why we might ask such a question or why we might want to do this, let's just notice for a moment we have a couple facts that we know. The sum of finitely many continuous functions is continuous. This is the ACT, algebraic continuity theorem. And we also know that the sum of finitely many differentiable functions has to be differentiable. That's the ADT, algebraic differentiability theorem. So the question that this then begs is, what about infinite sums? We know that we have some functions that can be represented as infinite sums. For example, you should probably be familiar with the power series representations of e to the x, sine x, cosine x. So to give you an example of that, I'll write out what we know e to the x to be. So this has a series representation. And if I write out some of the first few terms, this is what I got. So, for example, we know that e to the x has a power series representation as follows. It's the sum from n equals 0 to infinity of terms of the form x to the n over n factorial. This is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, etc. And the way that you generate this is by using the Taylor series formula. And this is centered around x equals 0. And what that does is it uses, Taylor series uses derivatives of the function, so the actual function value, the first derivative, the second derivative, the third derivative, etc., to slowly capture a closer and closer approximation of e to the x. So if I were to just take only finitely many of these terms, so let's say I was looking at a partial sum and I only summed up to this x to the third over 3 factorial component, then notice that that would only be an approximation of e to the x. But as we add more and more values to this, we're going to be getting closer and closer approximations of e to the x. And in that way, we can think of each successive approximation as a function in a sequence. So first, we're going to try to approximate it with 1. Then we're going to try to approximate with 1 plus x. Then we're going to try to approximate it with 1 plus x squared over 2 factorial, and we can continue this process, and that's a sequence of functions. And as we continue, it's been proven that that converges to e to the x, because we know when you take infinitely many terms, this is the power series representation of e to the x. So how does this link back to what I was talking about when I asked this question, what about infinite sums? Well, notice that in order to realize e to the x as an expression, as a series, we need to add infinitely many terms. And each of those terms, 1, x squared over 2 factorial, x to the third over 3 factorial, each of those are continuous functions. So we know that each term in our sequence of functions down here, each function that we have, is going to be continuous because it's just a finite sum of continuous functions. But notice that as we add infinitely many terms so that we get the actual function e to the x, we now have an infinite sum of continuous functions. Now, we know that e to the x is continuous, and so in this case it looks like an infinite sum of continuous functions should be continuous. But that's not always the case, and we need to start understanding what is it about the properties of the sequence of the functions, because continuity alone is not good enough to guarantee this. Another thing, if you wanted to see an example of differentiability, you might think about drawing a function that looks like a peak. We know that this function fails to be differentiable at the peak. We could call that C. So here's our function y equals f of x. But I could approximate this function using what are called bump functions. So first I could start by just using a function that goes straight across. Now this is not a good approximation, so maybe my next function I would want to use, here I'll use a different color. Maybe my next function I would want to use this one. Oops, that is not a different color. Here we go. And then maybe I want to do another function, and I get closer, and then another function. Here, we'll use this color. What I'm getting here are functions that are getting closer and closer to my function y equals f of x that is not differentiable, but each of these curves I've drawn is smooth, and so each one has to be a differentiable function. So like this is my f1 function, this is f2 in my sequence, here is f3, and then here is f4. And so if I take my sequence of functions, f1 of x, f2 of x, f3 of x, and I look at it, and so if I take my sequence of functions, f1, f2, f3, f4, and I continue to push them closer and closer to matching this peak, we expect that this is going to converge to my function f. Notice each fn is differentiable at c. However, f is not. Now, it could be that in order to get these approximations, what I'm doing is I'm adding another copy of a continuous function at each stage. So like f1 is my first function, and then f2 is really f1 plus a correction, and then f3 is f1 plus f2 plus, or sorry, f2 plus another correction. Getting closer and closer and closer, and so it's conceivable that each of the individual functions we're adding together are differentiable, but overall we're converging to something that has a peak, and we know that at that peak at the corner we fail to be differentiable. So this is showing us an example where sometimes things, just because individual functions are differentiable, it doesn't mean that the limit of those functions has to inherit differentiability. So the first thing that we need to understand in this section is, what does it mean for a sequence of functions to converge to some function f? Because we were just saying we've got this sequence of functions, f1, f2, f3, f4, and it's converging to f. Well, what does that mean? Right now, we only have experience talking about sequences of real numbers, and functions vary as you change the input that you're plugging into it. So let's, as a starting point, let's just remember what the definition of sequence convergence is when we're talking about sequences of real numbers. So again, here I'm thinking about sequences of real numbers. And ultimately, I'm going to be asking the question, what about sequences of functions? What does convergence mean here? So the definition of sequence convergence, remember, it's all about you have an arbitrary epsilon band, and your goal is to chop the tail of your sequence such that all the terms in your tail are within epsilon of the limit. Well, since we already know how sequences of real numbers work, and we know that functions output real numbers when you plug in a specific x value. The first step at defining sequence of functions converging is to just think about what if we fix a value of x and look at the corresponding sequence of outputs that we get. Then that reduces to a problem that we already know how to solve. So this is going to be the definition of what it means for a function to converge pointwise, or a sequence of functions to converge pointwise. So for each n in the natural numbers, we're going to define a function whose domain is A, and it's going to go to R. So every function in our sequence has the same domain. Then we're going to say the sequence Fn of functions converges pointwise on A. To a function f with the domain A also, provided for any x that we pick in our domain, if we generate our sequence of outputs in our function, so we look at fn of x, that's a sequence of real numbers, and we want to see whether or not that converges to f of x. So provided for all x in A, and we have for all epsilon greater than 0, there exists a capital N in the natural numbers such that for all n greater than or equal to capital N, Fn evaluated at x minus f of x needs to be less than epsilon. So this expression right here is like our an minus a, and an, the way we're used to it, is a real number, and if I'm evaluating my function at a specific x value, then I do have a sequence of real numbers associated with it, and whatever it converges to, my limit, I'm saying has to be the output of my function, f, that I'm converging to. So if I wanted to go back up here and think about how that looks graphically, I have this example that I've already drawn out. We're trying to make the claim that this sequence of functions, f1, f2, etc., is converging to my peak. Well, pointwise convergence says fix an x value and evaluate your function, each function in your sequence at that x value, and look at those points and ask yourself, do those points approach a specific function value? And it looks like they're converging to the point f of x on my graph. So these points I've drawn in here, it's f1 of x, f2 of x, f3 of x. And I need to be able to do this if I'm going to converge pointwise on the whole domain. I need to be able to draw this blue line wherever I want and see that I get convergence of the corresponding output values. So hopefully that makes sense. Again, here, I mean, just the way I've drawn this, it kind of looks like f4 is actually equal to f of x. But the point is we are basically creating a slice. We're saying fix an x, generate all the outputs of the function in your sequence, and then see what that converges to. Is that real number the output of a function f? If it is, well, then you have convergence to that value. Something important to point out here is that because we are choosing our x value first before investigating convergence, this tells us that as we change the x, the input where we're looking, the capital N that we need for our tail is going to vary also. So note, as we change x, capital N varies also. The notation that we use to denote convergence of a sequence of functions is Fn converges to F. Here we drop the parentheses. I think that's just a choice in terms of eliminating the number of symbols in the notation. So we write Fn converges to F. And we don't include the X because we just say Fn converges to F, and we add the qualifier that it's pointwise. So let's see if we can take a look at an example to figure out how this works. So let's let Fn be the function x to the n for each n. And we're going to work on the interval 0 to 1 closed. I want to determine the pointwise limit of my sequence Fn. So what I want to do is I want to determine, does this sequence of functions converge pointwise to a function on the interval 0, 1, and if so, what is the definition of that function? So to make sure we understand this notation, first of all, we are creating a sequence of functions. We've got f1 of x is just what you get when you plug in 1 for n, so we're just getting x. f2 is going to give me x squared. f3 is x to the third. And so overall, we're constructing this sequence that looks like this. And we're asking, what does that converge to? What's f of x? And notice we're thinking about this pointwise. Remember, you pick the actual value of x before you determine convergence. And so you can go through and you could say, all right, well, what would happen if I evaluated my sequence of functions at x equals 0? Well, looking at that without writing anything down, looking at the sequence, if I plug in 0, I'm just going to get the constant sequence. And so I expect that to go to 0 when x is 0. I need to ask the same question for all points on the interval 0 to 1. I would encourage you to pause the video and try to determine that on your own. I'm going to draw you a picture of what's going on. So what we have is a sequence of functions. We know that our first function is literally just the function f of x equals x. So we have the identity function. We got this straight line. Then our next function, so this is y equals f1 of x. And then our next function is x squared. So there's that. So here we've got y equals f2 of x. Our next function is x cubed. And what we see is that we're starting to get this like banana looking thing. And the way that it works is as we increase the value of n, we are going to stay closer to the x-axis for longer, but then we have to jump and make it back up to 1 by the time that we, y equals 1 on our graph, by the time x is getting to 1. And so plugging in some values, if I pick a number between 0 and 1, I'm essentially asking what is the limit as x goes to n, what is the limit of x to the n as n goes to infinity, where x is a point coming from 0, 1. Well, we know that that's going to change based on the value you plug in. If I plug in a half, for example, that's going to go to 0. If I plug in 1 for x and I look at that limit, I just have the constant sequence 1, and that's going to go to 1. So overall, my pointwise limit is going to be approaching this function that has a jump discontinuity in it. So my red function is f of x, and that is my pointwise limit. So the pointwise limit f of x, it's going to be 0 when I'm plugging in 0 or a number strictly less than 1. And it's going to be 1 when x is 1. And that just comes from computing the limit of our sequence of functions, thinking about how that changes as we vary x. Something interesting to point out here is that each of the individual functions that we had in our sequence was continuous. But as we converged to something with a jump discontinuity. This is an interesting fact that we're going to return to in our next video. So here we just want to note each Fn is continuous on 0, 1, but F is not. So the question is, what happened? Why did we lose continuity? We have convergence, but why did we lose the property of continuity? What's going on here? So that's going to be a question that we return to later in another video. But for now, what I want to do is I actually want to go through and I want to prove by definition that Fn for this particular example does indeed converge to the pointwise limit function that we've just defined. And in doing so, that's going to show us how, as we change x, capital N, where we chop our tail, is going to have to vary also. Okay, so we want to, for this particular sequence of functions, x to the n, and our function f that we just identified, we want to prove that this is actually the pointwise limit of 0, 1. And so we need to prove Fn converges to f on our closed interval 0, 1. So to do that, the first step is to just write out, well, what's our definition of pointwise convergence? It should be that for all x in our domain, which in this case is 0, 1, we should have that for all epsilon greater than 0, there exists a capital N in the natural numbers, such that for all n greater than or equal to capital N, Fn of x minus f of x is less than epsilon. Well, notice that the value of our function changes based on what x we're picking. So we're going to have two cases here. We're going to have case 1 where x is in 0 to 1, but not equal to 1. And then we're going to have another case, case 2, where x is actually equal to 1. Now, case 2, when x equals 1, we actually don't need to get into the definition of convergence, because when I plug that in, we know that Fn of 1 is 1 for all n. And so this sequence that we have is just a constant sequence, and that does converge to 1, which is the value of f of 1. And so we have convergence in that case. So we're going to focus instead on what happens with x values that are between, that are either equal to 0 or strictly less than 1. So in this case, what we're trying to make small is we're going to be looking at our function minus a limit of 0, because we know that f of x is equal to 0 based on our definition of our function. So really we're trying to say x to the n, we want this to be less than epsilon. Because x is non-negative, I can drop the absolute values and I really have this. I would like to be able to solve for n in this case, which requires me to take the natural log of both sides so that I can bring the exponent down. However, that begs the question, is the natural log defined? We know that the natural log is only going to be defined when we're plugging in positive numbers, but remember, we have a situation where x could actually be equal to 0 since we're including that. So at this point, we're going to have to assume that x is not 0, and this tells us that we actually need a third case. We want the case when x is equal to 0, but in that case, fn of 0 is just 0 to the 1, 0 to the 2, 0, etc., and that gives me 0 for all n. So there's nothing to prove in that case because it's just a constant sequence that converges to 0, and that is equal to f of 0, so we're good there. So now we need to go back up here and we need to amend our case 1. We're actually assuming now that x cannot be equal to 0, and that's so that we can take the natural log of both sides of this equation. So I get the natural log of x to the n has to be less than the natural log of epsilon. I know that's true because the log is an increasing function. I use my log properties to bring the exponent of n down. And then my goal is to isolate little n because I want to know how convergence depends on little n so that I can find where to chop my tail. So now I'm going to divide the natural log of x to the other side. In doing so, I have to ask myself, what happens to the inequality? Well, we know that x is between 0 and 1, which implies, if we look at the graph of the natural log of x, we know that it's negative when x is less than 1. So the log of x that we've just divided by is actually a negative number. So because it's negative, we're flipping our sign. So this is good news, though, because remember, we have control over making little n far enough down the line. We're trying to pick a capital N that's going to guarantee this constraint here. And this tells us we want to choose capital N such that capital N is greater than the log of epsilon over the log of x. We know we can do that by the Archimedean property. There's always a natural number bigger than any real number that you specify. So let's go through and write our proof up. So the first thing we're going to do is we are going to remember what we're doing. We are proving we're proving this highlighted form here. So the first thing we do is we introduce an x value. So we're going to let x be in 0 to 1. Now we know this breaks into cases immediately. So let's get our trivial cases out of the way. So case 1 is when x equals 0. Then we know that fn of 0 is going to be 0 for all n, just based on plugging into the formula, x to the n. So we have the 0 sequence that converges, and just to keep in mind, this is the sequence fn, evaluated at 0. That's going to converge to 0, which is the value of our function that we're saying is the limit of our sequence, and so that checks out. Do the same thing for case 2. Here x is 1. When you plug in 1 and you raise it to the nth power, you get 1 back out. So fn of 1 is going to be 1 for all n. So if I look at fn of 1, that's just 1, 1, 1, etc. That converges to 1, which is the value of the function at 1. So we have pointwise convergence there. Now we go to case 3. Case 3, we're going to consider x to be between 0 and 1. Here, we're going to let epsilon be greater than 0. And we said we need to choose our capital N in the natural numbers such that capital N is greater than log epsilon over log x. And we can do this since ln of epsilon over ln of x is a real number, because x, remember, is a valid entry in the domain of the log function. We know this n exists by the EIP, the Archimedean property. Now we are going to let little n be greater than or equal to capital N, and we're going to take a look at fn of x minus f of x. Now, because x is between 0 and 1, we know that we can substitute 0 for f of x, because that is the definition of our piecewise function. Right back up here. Our piecewise function is defined to be 0 for these x values. So I'm making that substitution down here, and then I am using the definition of my sequence of functions. Now, the fact that x is between 0 and 1 says that I'm non-negative and I don't need absolute values. So now I have x to the n. Making the connection to capital N is a little bit tricky. I know that connection comes from using logs. So what I'm going to do is I'm going to actually change this expression, and I'm going to say I need a different way of writing x to the n using log notation. Well, I know that this is really e to the natural log of x to the n. In this way, I have not changed the value. I'm still working with x to the n. I'm just changing the way that it looks. And this allows me to say, all right, I've got e to the n times log of x. Now, remember, log x is between, or x is coming from between 0 and 1. So the log of x is actually negative. And so if I were to instead replace little n with a capital N, I would be creating a larger number, because I would be multiplying a negative number by a potentially smaller natural number. So here I am using the fact that n is greater than or equal to capital N, and that log of x is less than 0. So if I multiply log x to both sides, I should see that I get this relationship, because the inequality, the sign changes. So this is actually less than or equal here. Now that I have that, I can make my substitution. I know that e to the capital N is even bigger than this log epsilon over log x expression. And again, using the same type of logic, because I know log x is a negative number, when I make this substitution, I'm only going to grow in size. Now I'm getting e to the natural log of epsilon, and overall that gives me epsilon out. Thus, Fn converges to F pointwise by definition. And that was kind of complicated because we had to do an algebraic trick in order to make our substitutions to see how epsilon comes out. It's not always going to be this complicated, but something I want to point out here is that the n value that we pick depends on the value of x. And so as we change our x value, the n that we're going to have to pick is going to change as well. And going back up here to our picture, notice that convergence, like if I'm looking at an x value, say right here, convergence of my function is going to take longer to get down to 0, because notice that my banana functions have points that are higher up, whereas if I had picked over here, look how much closer to 0 I already am just from looking at the first 4 functions. So I'm paying attention to this gap that I have right here. I'm much farther away from 0, and I'm going to have to increase n much higher. This is telling me that I need a larger value of capital N as x approaches 1. And that's consistent with investigating how this number behaves right here as x approaches 1. So notice n gets larger as x goes to 1. And that's just using the fact that the natural log of epsilon over the natural log of x is going to increase. If I take the limit as x goes to 1 of this, this is going to infinity. Because log x is equal to 0 at 1. So that's telling me that n needing to be bigger than that number is going to have to be pushed off to infinity. And in particular, as x goes to 1, capital N is going to have to go to infinity. It turns out that this fact right here is actually the reason why we end up losing continuity of our function. And that's what we're going to investigate in the next video for this section.